Okay, so in this video, I'm gonna go through some electronics fundamentals that you need to know. Um, that you need to know. So, first up, right, you need to know how electricity flows in a circuit. So, um, this is a this is a circuit, right? And then we have this component here, this symbol, and this is actually a battery. So this is a battery here. This is a battery, and then you see these black lines. This is a wire. Okay, so electricity, or the current flows from positive to negative. So in this battery, right, there is actually positive, which is here on this longer side, and negative, which is on this shorter side. So as I just mentioned, current flows from positive to negative. So it flows like this in an anti-clockwise way. Um, Something that you may not need to know is that the actual electrons flows the opposite way. Okay, but that's like a tidbit lah. You don't need to know this. What you need to know is that current flows from positive to negative like this, and you will be using that concept to solve all other kinds of questions. Okay, so you need to know this. um yeah, so I'll just put this here. Okay, next, components eat. Okay, so let's say I have this circuit, right? Battery here, resistor here, another resistor here, and then it closes. Okay, what I mean by components eat, right, is that the battery, right, actually provides a voltage for this circuit. And what the voltage does, right, it is that it pushes the electrons, or it makes it so that current moves. Okay, oh, I forgot to mention, right, when there is no path from positive to negative, current won't flow. So like if it was this if it was this, there's no obvious path, that there is no path from positive, which is here, to negative, so the current just won't flow. Okay, okay, so in this case, right, as I was saying, voltage makes the current move. Oh yeah, and what I just mentioned, let me just leave this here. What I just mentioned, this is an open circuit. Yeah, it has a name. So this is a closed circuit, this is an open circuit. Yeah, sorry. I'm kind of rushing through this first because this is honestly, right, for you watching, you probably actually already know this. So yeah. Okay, anyway, in here, right, the voltage makes it so that the current is active, like there is a current. And with these symbols here, these are components, right, and this is actually a resistor. Yeah, the resistor will actually take up a part of that voltage to function. So like let's say there's 5 volts here. um the resistor will actually eat up some of that voltage. So just as an example, this particular resistor takes up 3 volts lah. So now flowing through here, so originally flowing through here, there's 5 volts. Now flowing through here, there's 3 volts. Wait, oh no, 5 minus 3, so it's 2 volts. So there's 2 volts left for this to function. And then let's say it just takes up all that and eats it, so to function, then there's 0 volts, then it closes, and then yeah. So yeah, components eat up voltage to function. Okay, um next is, okay, the order's kind of wrong here, but actually I forgot to write something, but I'm going to talk about it now. I'm going to show you um most or all the symbols of for components that you need to know. Okay, so let's just start. Okay, I know I'm saying this stuff. So first is the wire. Okay, as I already said, wires connect components together. So the wire, uh yeah, it connects components together, so that's that. The next one is the battery. And what the battery does is that it provides voltage to power a, a circuit, or to like provide a current. Yeah. The next component is the resistor. Okay, in all my videos I will be drawing the resistor like this because it's accepted in the engineering community as such. However, for the O levels, you're gonna see it drawn like this as a bar. Okay. In the O levels, it is with of utmost importance that you draw your resistors like this. Do not draw it like this. Do not draw it like this. This is how you're supposed to draw a resistor. Okay. Don't ask why. All right. Next is the LED. Or okay, next is the diode. All right. I will be drawing the symbols, but I will not be actually I'll not actually how do I say, explain what the component does, except for like the wire and the battery. So there is a resistor video, you can go check it out. There's also a diode video, and you can go check that out. Okay, next is the capacitor. There are two versions, the polarized and the non-polarized. So it's like this. Yeah. um then we have what else do we have? Oh, we have our switches and buttons. So the switch is like this. And there's a few kinds of switches actually. This is called the single pole single throw. This is called the single throw double throw. Single throw dual. Wait, what? Single pole. Oh shit, yeah. Okay, this is called the single pole single throw. Single pole dual throw. There's like dual pole dual throw, but I'm not gonna talk about that because you don't really need to. Okay. And then now I'm gonna talk about buttons. So you have push to push to make, which is like this. Push to break, which is like this. Okay. um yes. Oh, what else is there? Oh, now we have like, okay, other than this diode we also have the LED. So what it is just like a light. It lights up. And we also have the bulb, and it looks like this, the bulb. Yeah. Next we have the voltmeter, which is like this, and the ammeter, like that. Right. Okay. Oh yeah, sorry, the single pole dual throw has like, it's like this, sorry. um what else? I think that's like the basics. There's others, but I won't really talk about them now. Like for example, there's like, it's like logic gates, right? But I'm not gonna talk about it now because yeah, nah. So these are like the main ones, like the main characters. For like the other ones, there'll be like specialized videos for them. um oh, I guess I should also talk about like the transistor. So like the transistor, right, there are two types, NPN and PNP. And it's very important that you properly you properly demonstrate, not demonstrate, you properly draw them. Yeah, because if you anyhow draw, right, then it would mean that it's an NPN, or it will mean that it's a PNP. Okay, so for NPN transistors, which is this one is an NPN transistor, the arrow is actually going out from this line, and for PNP the arrow is actually going in to the line. Yeah. So yes, yeah, 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 it goes into the line. Okay, cool. So that's transistor. All right. um that's simple. So I'm gonna move on now. I'm gonna move on to okay, let's make this smaller first. Okay. Yeah, so the order is wrong here. I'm actually gonna move on to V equals IR now. Okay, so what is V equals IR? V equals IR is an equation that relates voltage that we've talked about to I and R. Okay, what is I and R? I stands for current and R stands for resistance. So what is I? What is current? Well, we've actually talked about this already. So current is like, I guess you could say it's the speed at which like electrons is like pushed out. Yeah, it's like kind of like the speed. And resistance is how much um the current is resisted. That means how much is like pushing back, you know. So yeah, that's V equals IR. That's what I and R is. So for these three symbols, right, there's actually units for them. For V, for voltage, it's V. For I, it's A for amps. And for R, it's ohms. Okay. So if I say like, oh, this battery has like 10 volts, you just say 10 volts. And if you say, oh, the current is 0.2 amps. Oh, the resistance is 10 ohms. Okay, so that's V equals IR. Oh, and this equation basically relates the current and the resistance to voltage. So the product of I and R of current and resistance is voltage. Okay, so that's V equals IR. Then now we move on to power. Okay, so it says P equals VI there. But what it is basically is the equation that demonstrates power. So what is power, right? Power in in watts is the product of voltage and current. So yeah, that's power. And there's one specific thing, right, is that all components have a specific power rating. So like you may see some resistors with a power rating of I don't know, 1 watt. I can't write. That was weird. One watt. Yeah, 1 watt. So what this means basically is if the power like that is powering this resistor exceeds 1 watt, the resistor will break. So that's a power rating. Okay, and this is how you find it lah. You may also notice, right, that I can actually there is not power is not just the product of V and I, because we can actually replace V with IR. So this could also be I squared R. You know what I mean? And we can actually replace I with V equal over R, because if we just rearrange this equation, right, we actually get this. So instead of Vi, we can actually also say V squared R. So yeah, there's just different forms of power. And then now we come to energy. Okay, so energy is equals to power times T, which is time. So power is actually in joules, P as we know is in watts, and T is in seconds. Okay, so energy is just like, oh, how much energy is it using in what time frame, you know what I mean? So yeah, and we can demonstrate this in a different way. We can say, oh, VIT. So I'm just replacing P now, and then we can just use all these other expressions here. So it can also be this, it can also be this, V squared T over R. It can also be this, yeah. And these different expressions will actually come in handy for some specific questions. Okay, so I kind of just taught you like 50 trillion things in like 4 seconds without any application, and I think it doesn't do justice. It doesn't, yeah, it doesn't bring actual justice on the concept. So I'm gonna create a question now. All right. And then once I'm done creating this question, I will once I'm done creating this question, I'll pause. I'll tell you. Oh, you can pause the video now, and you can try it out. Oh, I'm just remembering. Um, Power actually has a different representation, which is actually E over T. Okay, and it's just using like some expression from this into that. Just know that power can also be E over T. Okay. Anyway, let me create a question now. So first, I'm gonna test about V equals IR. So I'll just make a basic question. So we have a battery here. We have a resistor here. Okay. Oh, you know what? I should decrease my thickness. Sorry about this. Yeah, okay. So, um, okay, so this is the question. All right. You have this circuit here, and then right, find the current. Okay, very simple. Find the current. So you can pause here right now, to try and figure it out yourself. Okay, so we know V is equals to IR, and we have two of these values here. So we can just sub them in. So V will be 6 volts, I will be I. We don't know. We're trying to find I, and then R is 10 ohms. So very simply, we can find I by dividing both sides by 10. So the answer is actually 0.6 amps. So in this circuit, the current is 0.6 amps. Yeah. Alright, so that is the first question. Next question, oh, about power. Okay. Um, okay, let's just use this. Let's just use this same thing here. So now, my question for you is, knowing that it is 0.6 amps here, how much power is needed to power the resistor? So you can pause here to try and figure out yourself. Or rather, how much power is like being pushed out of the resistor? Okay. Anyway, I'm going to assume you have unpaused or paused or whatever. What am I saying? Alright, so again, we know the equation P is equals to VI. So we can just sub in V and I, which is 6 volts times 0.6 amps. Okay. So we just plot this, we just calculate this, and we find that we land up with 3.6 joules. So that's the amount of power that's being dissipated in this circuit. Alright, last question. Um, in in uh in a minute, how much energy is used? So you can pause now. Alright. So we know the equation E is equals to P T. So we can just sub in the values 3.6, and I said a minute, and in a minute there's 60 seconds, because we need to convert from minutes to seconds because T is in seconds. So T would be 60. So we can actually find the amount of energy that is used, and the answer is 216 watts. Oh, P is in watts. Sorry, power is in watts. Yeah, if you caught that mistake, kudos. So uh yeah, so if you got these answers, then you understand really quickly, and good job to you. Yeah. Okay, so that is V equals IR. That is voltage, current, resistance, power, and energy, and time, I guess. So let me just make this a little bit smaller. All right. Okay, what's next? General calculation. Oh, okay. So before this, right, I actually need to teach about um numbers. Okay. So in electronics, right, or in just general mathematics, you will have things like numbers like this, like 36000000 amps. Sure. Okay. So that's a lot of amps. So what engineers or what mathematicians or just regular people do, right, is that they like decrease the size of the number, but it still retains its magnitude. Okay, let me just show you what I mean. So right now I'm doing something called I don't actually know, but what I'm doing is basically like converting this number into a standard form. Okay, so the fact that you're watching this video, I would assume that you know like what a decimal point is. So like 123 dot 3456. What this does is basically, right, the decimal is here, and then I'm bringing the decimal up to this point. So then to put it in standard form, right, we count how many times it moves, which is 1 2 3 4 5 6 7 6 7 6 7. So the magnitude will be 7. So this is representing 36000000 amps, but in smaller. Okay, so why is this important? Because in okay, this bit here can actually be represented with names. Okay, well, not this exactly. There are specific names for specific magnitudes. For example, times 10 to the power of 3 is kilo. Okay, or like times 10 to the power of negative 3 is milli. So basically you need to know, yeah. So okay, I'll just show you all the rest. So there is deci, centi, milli, and then it skips to 6 for some reason. Deci, centi, milli, micro. Then we have 9, which is nano, and then we have 12, which is pico. That's all you need to know for O levels. Let me shift this away. And there is actually a unit for this, not just a name. So deci will be D, centi will be C, milli will be M, micro will be this thing. I forgot what this is called. Nano is N, and pico is P. Okay. Now for this. Okay. So kilo is 10 times 10 to the power of 3. For times 10 to the power of 6, there is actually mega. Okay, times 10 to the power of 9, there is giga, and times 10 to the power of 12 is tera. Yeah, so okay, let me move this again. Now for this we have the symbols as well, and that would be kilo would be K, mega would be M, giga would be G, and tera would be T. So yeah, it's pretty simple. um okay, so before I go on, right, let me just do a practice question. So let's say I have this number 3.6 times 10 to the power of 12. Okay, this is a question to show you how it's done. So don't pause the video because I want to show you how to convert this into normal, like regular form. Then after that, I'll do a few questions and then you can pause the video then to try it out yourself. Okay, so for this, right, you would be actually moving the decimal point backwards 12 times. 12 times, huh? So let's go ahead and try that. Okay, so it will move back 12 times. So from here originally, 1 2 3 4 5 6 7 8 9 10 11 12. Okay, so this is actually the number, which is 32 tera something, I don't know. Yeah, so this is 36 tera. Yeah. um And actually this is 33.6 T. So basically you have to convert the T from T to the times 10 to the power of 12, then you have to do this to get it back to this. So let me give you a question now. Convert this into like normal. So you can pause the video now. Okay, so for kilo, it's actually times 10 to the power of 3. So we need to move the decimal point 3 times back. So let's do that. So it will be 1, 2, 3. And then the answer is 7,200. Yeah. Let's do another one. Let's do 6.9 uh, micro. Okay, so let's try that. I mean, you can pause the video to try that. All right. So 6.9 micro is actually equals to 6.9 times 10 to the power of negative 6. So for this, we've been dealing so far with to the power of positive numbers. For negative numbers, you move the decimal point to the left. So we need to do that 6 times. 1, 2, 3, 4, 5, 6. Okay. So in this case, the number is this. Like this. Alright. Let's do like one more practice, okay? Let me give you this number. Okay, the question is represent this number using the kilo prefix. Okay, so the kilo prefix would be actually times 10 to the power of 3. So in this case, we just move the decimal point 3 times. 1, 2, 3. So the answer is 3634 times 10 to the power of 3. And then the question was demonstrated in kilo prefix, so it'll be 3634 kilo. Yeah. Okay, in summary, right, when you see like there is a positive power on times 10, then you move to the right. And then if it's negative, you move to the left. But if you want to convert a normal number to standard form, then you just go into the opposite direction of how you normally would for that power. Yeah. Okay, so that's that. Now, let me give you a test. But let me make all of this smaller first. Let me give you a test. So, let's say I have this, alright? I have this circuit. Okay, it's very simple. This is 6 kilovolts. And then the current is 200 microamps. So with this, right, can you find me the resistance? What is R? So this is a test question. Pause the video now to try and do it out. Do it yourself. Okay. Okay. So first, let me show you how a student who is unfamiliar with what's going on will approach this question. So they'll be like, okay, I can use the V equals IR. I can sub in the values, so it will be 6 kilovolts is equals to 200 microamps times R. So then R would be 6 divided by 200. So we get out our calc and then we just put it in. And we find that the resistance is 0.03 ohms. Okay, if you did this, you are wrong and you should pay attention right now. So basically, this approach is wrong because this kilo prefix, this micro prefix, actually changes the magnitude of the number itself. So once you see in your calculation, right, that there is a prefix like kilo or micro, convert it back into the times 10 thing. So 6 kilovolts would actually be 6 times 10 to the power of 3. And then 200 micro would actually be 200 times 10 to the power of negative 6. So to find r, it would actually be 6 times 10 to the power of 3 divided by 200 times 10 to the power of negative 6. So this now is correct. And then we put this in our calculator. And we find that the resistance is actually 30,000,000 ohms. So the resistance is very large. Um, just for fun, right? Convert this into such that it will be 3 prefix ohms. Prefix, not the times 10 thing. Prefix. So you can pause the video now to try. Okay. Let's see if it works. So so I'm going to move the decimal point to the left. 1, 2, 3, 4, 5, 6, 7. So if you have correctly put that it cannot be put in a prefix because there is no times 10 to the power of 7 prefix. As you can see, right, there's only times 10 to the power of 6. Then you get a gold star. So it actually can only be written as 30 mega ohms because times 10 to the power of 7 there's no prefix, so you just go for the next best thing in if this happens, which is mega. So okay, that's this. And that is what I want to talk about calculations. So when you're doing calculations and you see the prefix, convert it back into the times 10 thing so that you don't screw up. Okay, now let's talk about circuit theories and voltage like rules and current rules. Okay, so let's talk about current rules actually, okay? So let's say I have a circuit, right? And then there's like wires going all over the place and they all connect at this one node. So let's say like, oh, there's a current going in this way, and there's like a current going out this way, and a current going out this way, and a current going in this way. Okay? And then let's say, oh, this is 6 amps. Oh, this is 4 amps. Oh, this is 3 amps. Oh, this is 1 amp. Oh, this is 5 amps. Okay. Um, Now, right, I will be teaching you something called KCL, or Kirchhoff's current law. So basically, Kirchhoff's current law states that the current going into a node is equal to the current going out of the node. So in this case, current going out of the node, right, is 4 amps. Oh, okay, yeah, I made a mistake here. Sorry. So like this would be like um this in this case, okay, this has to be 0 amps lah. Wait, what am I saying? Oh yeah, this has to be 0 amps. So current going out of the node is 4 amps plus 3 amps. Current going into the node is 6 amps plus 0 amps plus 1 amp. So it will be 7 amps is equal to 7 amps, and then we see that this holds out true. So KCL's law, to summarize, okay, states that the current going into a node is equals to the current going out of a node. So knowing this, right, let me give you a example question. All right, so we have this here, this node, and then we know that there are things going in and there are things going out. Okay, so let's just say going out is 6 amps, this is 4 amps, this is 0.6 amps, and then this is I. Okay, the question is find I. So you can pause here to try it out for yourself. Okay, so using KCL, we know that the current going into a node is equals to the current going out of a node. So going out is 6 amps, and going in is 0.6 amps, 4 amps, and I, which we're trying to find. So this is just a very simple question. This would be 6 minus 0.6 minus 4, like this. So 6 minus 0.6 minus 4, and we find that I is actually 1.4 amps. Alright, so that's that. That is KCL. Now we're going to move on to KVL. And KVL is slightly more complicated than KCL. So actually, I'm going to do a brief explanation on KVL here, and then I think I will be making a separate video on KVL itself with a lot more examples and questions, because this video is really long as how it stands right now. So KVL basically is, let's say you have this circuit. So you have this circuit, and then there's like a resistor here, another resistor here, and then yeah, that's pretty much it. So KVL is basically um, trying to relate voltages to each other. So this is, let's just call this VCC, and this is R1, and this is R2. Remember how I said like components eat up voltage? R1 eats up V1 voltage, R2 eats up V2 voltage. Okay, so KVL is a law, but I feel it's more like a process. And what it does is that it relates components that emit and absorb voltage to each other. So I'm going to show you how to do the process. Okay, so in a normal question, right, you'll see something like this, right, and then you see A, B, C, D on like these like parts where the wire bends, and then you'll see, and then the question will be something like, oh, in the loop, they'll use the word loop, A, B, C, D, A, form an expression, something like this. Okay, so first step, right, is you look at the question, and and then you see, oh, okay, so from A to B, from B to C, from C to D, and then from D to A. So you're going to be going in this direction, okay, in this anti-clockwise direction. Then the next step is you look at the batteries. So you see, oh, this battery, right, the charge here, this is positive, this is negative, as I already explained like at the start of the video. And then you look for the components. All right, for components, right, as you follow the direction of how the loop was told you the direction is, when you enter a component, so like now I'm entering this resistor, you enter as plus, and then when you exit as minus. These plus and minus here will be helpful later. Okay, so now we're following along, la 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 la, we enter a resistor, and then, oh, okay, we enter plus, we exit minus. Then once we complete the loop, because it ends at A, we're done. Okay, but we haven't solved the question. The question is form an expression. So how do we form an expression? We follow this ABCD loop again. We start A, and then we move, and then we enter this battery, and we exit. As you can see, when we exit, the symbol here is plus. So we write down plus VCC. Okay, this will all make sense later. Let's move on. La da 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 da. We enter the resistor, and then we exit as a minus. So we write R minus R1. Okay. Then we move on. La da 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 da. We enter R2, and we exit R2 as minus. So we write minus R2. Then we continue, and we see no components, and we end at A. Okay. What we have done is we have created an expression, but this doesn't really help us. Once you're done finding the expression by going through the components, what you just wrote is equals to 0. Okay, so that is the expression. VCC minus R1 minus R2 is 0. Oh, sorry, I meant to say not R1 and R2, I meant to say V1 and V2. Okay, so how does this help us at all? This helps you solve the question and get the marks. And yeah. Um, okay, you may say, okay, this doesn't make sense at all, because it's just like, this is just like in theory. But let me show you why it makes sense. If we rearrange this formula, we get VCC is equals to V1 plus V2. So if we look at this circuit here, the battery is actually putting out voltage, right, that's being used by both R1 and R2, V1 and V2. So therefore, it's sensible to say, V1, which is the amount, the voltage that R1 eats, is equals in that voltage added with the voltage that's eaten up by R2 is actually equals to VCC. So it does make sense, okay? And this is KVL. So let me give you one more practice question, and then I'll just end with a few more closing notes, because yeah, I'm reaching the end of the video. So let me give another practice question. So in this question, we have V1, V2, V3, V4, and V5. Okay, and then the loop goes like this: A, B, C, D. And then the question is, in the loop A, B, C, D, A, form an expression. So you can pause now to try and do it. Yep. So go ahead. Okay. So first step is you look at the circuit and you say, okay, A, B, C, D, A. It flows. The current flows. The direction flows like this. So you say, okay, okay, anti-clockwise. Next is you label the batteries. So longer one is plus, shorter one is minus, like this. And then now, last step. Okay, not last step. Okay, last step in analyzing, I guess. You go from A, you follow, and then when you enter a component that's not a battery, you enter as plus, you exit as minus. So we've done the battery already, so we skip and we go here. Okay, enter as plus, exit as minus. Goes with this resistor, enters plus, exit as minus. This is a battery, so we skip, and then we reach back to A and we're done. So now let's create the expression. So we start from A, we enter a battery, and we exit as minus. So we write down minus V5. We enter a battery, we exit as plus, so we write down plus V1. We enter this resistor, we exit as minus, so we write minus V2. We enter this resistor, we exit as a minus, so we write minus V3. We enter this battery and we exit as plus, so we write plus V4. And then we reach A and we're done. Last step, we write equals 0. So if you have this expression right now, then you are correct. And we can rearrange this equation to make a little bit more sense. V1 plus V4 is equals to V2 plus V3 plus V5. So these two, okay, what this is saying is these two batteries is providing voltage for all these, and it's like getting eaten up, nom nom nom. Yeah. So that's that. That is KVL. So I've taught you quite a bit of fundamentals. We started off quite slow and then we moved on to something a lot more complicated. So I apologize for that kind of inconsistency of the level of the video. I also apologize that this video has not been structured very well. I didn't really prepare a lot beforehand for this video. So if you have watched until here, I thank you for your patience. Um, a few closing notes. I forgot to mention a few things. In my other videos, I will be, instead of drawing circuits like this, I'll actually go at them like this, like plus 5 volts. Then I'll have like an LED or a diode or whatever, and then this thing. So what this is power, this is ground, and you can imagine it like this. There's a diode, right, and it's connected like this, and there's a battery. So this 5 volts corresponds to this, and the ground is like completing the circuit back up. Yeah, that's my final closing note. And with that, I do believe I have covered much of the fundamentals of electronics that should help you understand and comprehend the next few electronics videos in my videos and like other electronics concepts. So yeah, that's it.